folks, this is Mr. H, and I have the Tablecloth Demo set up and ready to go here. So this demo is an excellent example of Newton's first law, which of course says that an object at rest has the tendency to stay at rest, object in motion has the tendency to stay in motion. So currently I have two bins here that are, as you can simply see, at rest. The goal of this demo is to slide this tablecloth out from under my bins, my objects at rest, without disturbing them or making them fall off the table. So let's go ahead and quickly demonstrate what this looks like, and then we'll talk about what actually happens. So I will go ahead and I'm going to pull the tablecloth out from underneath, and we'll see if the bins will actually stay in place. 3, 2, 1. Okay, not too shabby. The objects hardly moved at all. So how, I might ask then, is this a demonstration of Newton's first law? Well, as you can see, I was holding only the tablecloth, okay, and the objects, the bins here, sat on top of the tablecloth at rest. As I pull on the tablecloth, okay, these objects have inertia, they have mass, they have the tendency to stay at rest. As I pull on only the tablecloth, there is some slight friction, some pulling underneath on the bin, but the bin has the tendency to stay at rest. Okay, it's going to resist, right, that pull. So as I pull the tablecloth out from underneath, it remains at rest because it was already at rest because of its inertia. Okay, so again, you can try this at home. The recommendation would be try to find something, tablecloth, that is relatively smooth, that will lower the amount of friction between the objects and the tablecloth. And don't use your mom's fine china because this does take a lot of practice, and there's a good chance you might break an object here or there. Okay, so thanks for watching the tablecloth demo, and we'll move on to the next one. All right, physics, this is Mr. Henderson back at you again with another Newton's first law demo. The point of this demo is to show you inertia, right? An object that has mass has inertia, and that's the resistance to change. So an object in motion has the tendency to stay in motion, an object at rest has the tendency to stay at rest. So this is the stake and block demo. I have a stake that is basically put through a block, right? And the block is movable, okay? It can move up and down the stake. And I have a hammer here. What I'm going to be doing is I'm going to drive downward on the stake, and I'm going to push the stake down through the block, and the block should appear to rise up the stake, but I'm not touching the block at all. Okay, the block is simply just here, right, resting around the stake. It's completely movable, okay, but I'm not going to touch it. So what's at play here? Well, I will be acting on the stake, pushing the stake downward. The block has inertia. It's resisting this downward change. So the stake is going to be forced downward, and the block is going to try to maintain its position in space. It has inertia. It's going to resist that change. Okay, that's Newton's first law. So let's see what happens when the block resists the change and I apply the change to the stake. Here we go. The block started at the bottom and is now at the top. We'll go one more time. Here we go again. Again, the block has appeared to move from the bottom to the top, but really what's happening is the stake is the object that's moving as I drive it downward. The block is resisting, the block is maintaining its position, and the stake is what is moving downward. It's an illusion. Okay, there you go. Just another illustration of inertia in action. Thank you. All right, folks. So for our next first law demo, I'm going to illustrate the quarter catch trick, or the elbow quarter catch trick, in which I will stack up, I got about 7 quarters here, a stack of 7 quarters. I'm gonna go ahead and take these, stack them up on my right elbow, and in one motion, swoop through and catch those quarters. So let's go ahead and just illustrate it first here, and then we'll kind of see how it's done. So you can clearly see the quarters at rest on my elbow, and I'm going to swing my hand through in one motion and catch those quarters. 3, 2, 1. There they are. So what happened here, and how does this illustrate Newton's first law? Well, if you take a look, again, at my quarters, they are clearly at rest on top of my elbow. And what do we know about an object at rest? Well, it has the tendency to stay at rest. In one motion, I dropped my elbow below the quarters, so my elbow is moving, and then the quarters are resisting that change. They maintain their position. In that same time, as my elbow drops out, my arm moves through, okay, and grabs the quarters before they can fall very far at all. They hardly move, okay, because they're resisting, right, that motion. They have inertia. These quarters have mass. They resist change. So here we go again. 3, 2, 1. There are your quarters. Let's go ahead and watch it again one more time in slow motion. All right, folks, so for our next demo today, we're gonna use something called the hover puck. Okay, it looks like a soccer ball. It's meant to be, pushed around on the ground. You can, play a soccer match with it, I suppose, right? So here's my soccer ball. Let's say I'm gonna give it a go, give it a push here, right? Kind of lame, doesn't do much. It just kind of stops. Why does it stop? Well, because of this thing called friction, right? And friction, over time, slows this soccer ball down, and it comes to a rest, okay? You see this a lot, right? If you're in your car, you're cruising down the road, you don't push on the gas, you don't push on the brakes, your car is eventually going to come to rest because of friction. You're on your bike, riding your bike, right? Eventually, if you stop pedaling and you just coast, you will come to a stop because of friction, okay? So this idea of Newton's first law, an object in motion stays in motion unless acted on by an outside force. Okay, what does that mean? Well, that literally means an object will continue on in a straight line path with its velocity that it has indefinitely until an outside force acts on it, like friction, okay? So if I can give this a push and there was no friction, this puck would continue on in a straight line path at its velocity indefinitely until something acted on it. Maybe a person, maybe a table leg, maybe the walls, I don't know, something, right? So the cool thing about this is, well, there's a fan on the bottom. Just like a hovercraft, if you've ever seen a hovercraft, right, it allows objects to float on a pocket of air, which reduces friction quite a bit, or can completely eliminate it. So if we turn the fan on, it's quite loud, but what we see is that now, if I give it a push, it maintains a constant velocity. Now this table is not level, right? So we're gonna have some issues with some gravity acting on it, causing it to change its path and its velocity a bit, or its speed a bit rather. But again, you can see it continue to move in a straight line path. So what if I had a longer distance to work with? Could we take it and make it go indefinitely, 100 feet, 200 feet, 300 feet? Sure, if we had a nice, flat, straight run to do that. So let's go ahead and take it to a longer stretch run and see what sort of results we can get. All right, guys, so here we are, we're out in the hallway. We have a nice stretch run of hallway here to go ahead and get our hover puck going. So I'm gonna go ahead and lay it down, give it a steady push. I want you to keep an eye on it. Does it maintain a relatively constant velocity? That means, is it maintaining the same speed? Is it maintaining the same direction? Okay, because in an absence of an outside force, an object in motion will continue in motion. It will continue its state of motion it is in. So let's go ahead and give it a push and let's see what happens. and now it is acted on by the wall, and it stops, and it's coming back towards us. Again, so you can see as we eliminate that friction, it allows that object to maintain its state of motion. Its inertia allows it to continue forward at a constant velocity until it was acted on by the wall. Thanks for watching. All right, folks, welcome back to another Newton's first law inertia demo. This one is going to be the magic hoop trick. And the goal of this trick is to place, right, so I've got a glass jar here. I'm going to place a hoop on top of the glass jar, and then I'm going to rest an object. So in this case, I've got a battery. Okay, I'm going to rest a battery on top of the hoop. And the goal is to remove the hoop and allow the battery to simply fall right underneath the hoop and into the jar. Okay. So this seems to be like a trick to it. Is it some sort of like a magic trick? Is it like is there some unknown science behind it? And the answer is no to all of that. Okay, we're simply going to use Newton's first law to make this work. Okay, an object at rest stays at rest. An object in motion stays in motion. So number one, if I am trying to pull this hoop out of the way, okay, the object that I'm going to be acting on is the hoop itself, okay? The object at rest that's going to remain at rest is going to be the battery. Okay, it's going to be the battery. So if I take the hoop and remove it quickly enough, the battery will remain at rest. It will not deviate from its position, right? It will remain at rest. It's not going to go forward, backwards, left, right. It's not going to go anywhere. It's simply, once the hoop is gone, going to fall straight down into the glass jar. Okay, that's the first part of this demo. Okay, the second part is equally important. The second part is how you remove the hoop. There are two different ways you can go about doing it. Okay, you can pull the hoop from the outer edge, right? So you can essentially push one way. So I could grab here and push that way. Okay, or I could go off from the left side and push that way. Okay, or the other option is you can go from an inner edge. So you can go here, push from this inner edge, or here. And there is only one correct choice to make if you want to be successful in this demo. And the correct choice is pulling from the inside edge, pulling from the inside edge. Here's why. If you pull from the inside edge, what happens is this side of the hoop gets acted on. This side is at rest. It's not being acted on right now. It's still at rest. It's maintaining its position. It has inertia. If this side remains at rest and this side is moving, it creates a small strain in the hoop. Okay, and I'm pulling, I don't know if you can see it, but the hoop itself actually narrows in this direction. Okay, if the hoop narrows in this direction, okay, a small gap between the hoop and the battery is created. Very small, okay, but small enough that if you're quick, you can pull the hoop right out from underneath and the battery will simply fall. Okay, so you have to go from the inside edge because the inside edge creates one side that's moving, the other side that's not, and in doing so, right, creates a strain so that the hoop flattens. Now, what if we go the other way? What if we go from the outside edge and push through? Here's the problem with that. If I go from this edge, I'm going to be pushing this side this way. The other side that I'm not interacting with is at rest. So if I push on this side and this side's at rest, I create another strain in the hoop. But this time, I don't know if you can see it, the hoop is actually pushing upwards, okay? It's actually pushing upwards. So the strain is this way, okay? That creates a springboard effect for the battery. It actually will push the battery up. It makes the battery jump. That, combined with me sliding the hoop, creates an effect where the battery will jump in an unpredictable manner. So let's go ahead and test this out. Let's do the incorrect method first and see if that does actually put the battery somewhere outside of the jar. Okay. 3, 2, 1. So yeah, you can see that the battery actually launched. It was here, and then it was up here, okay? Because, right, this side of the hoop was in motion, this side of the hoop was at rest. It created a spring effect. It pushed it upwards. So let's see if we get a difference by going from the inside edge. Okay, so I'm going to pull from the inside edge. That should set this side into motion. This side will be at rest, and it will pull the hoop this way and cause it to compress. creating a slight gap between the hoop and our battery. The battery should fall straight through. 3, 2, 1. So what we should see there is, again, I pulled the hoop through. That battery remained dead still. It simply dropped vertically straight into the container. There was no springboard effect because in my motion, right, I pulled on this side is at rest. I created that small gap between the battery and the hoop, and I got the hoop out of the way before the battery could start moving, and the battery simply fell straight down into the container. Okay, so I've got my spinning eyeball. Why is this thing spinning? It's spinning because I am applying a force to it, causing it to constantly remain in motion. The string is pulling, right, on the ball, always pulling it inward, right? So if the ball is going this way, it's being pulled in, causing it to turn. Right, if the ball is here, it's moving this way, and it's being pulled in, causing it to turn. Okay, the ball is being pulled in, causing it to turn. Ball rotates around, moving this way, the rope pulls it in, causing it to turn. So the ball is always changing its velocity, right? Even if I keep this right at a constant speed, its velocity is always changing. Okay, so what would happen if I let go of the spinning eyeball? What happens if I let go of it at any different position? Well, depending on where I let go of it, that dictates where the ball will go. So what we're going to do is I'm going to show you a couple different shots of this in slow motion. Okay, as I rotate around, okay, if I am right here, right, the ball is moving this way. So if I let go, the ball will continue to move this way. Okay, as my ball rotates around, it's right here, right, it's moving this way. So if I let go, when the ball is here, it's going to move this way. Okay, as the ball swings around, when the ball is here, it's moving this way. So if I let go, it's going to move this way. Why would that be? Well, of course, because an object in motion will stay in motion unless acted on by an outside force. So this object at this point is moving in this direction. If I take away the outside force is the string. That's what's causing it to change its direction. If I remove the string, the object will move in a straight line path at the velocity it was moving, right? At the speed it was moving with a constant velocity until acted on by an outside force. It will get to the floor eventually, right? Because of gravity. So what we're going to do is I'm going to show you a couple different examples of me spinning this and then letting go, and we'll determine where the ball will go depending on where I let go.